Okay, so for this question, it asks us to talk about the movement of fluids in and out of the capillaries. And so this is what we know as capillary exchange. So what we'll do is go ahead and talk through each one of the pressures. So the first pressure that we'll talk about is called hydrostatic pressure. And that is the movement of liquid in and out of capillaries. And we also have net osmotic pressure. And that is describing the movement of solutes in and out of the capillaries. So we'll go ahead and highlight the different kinds of pressures that we see. We'll label this diagram. That will be the best way to describe it. Okay, so we will start on the artery side of the capillary and talk about the movement of fluid in and out. So first we know we will have our HP going out, our hydrostatic pressure, and then we will, these little white dots right here represent proteins in the blood, most likely albumin, and so we have another pressure that is called BCOP, which is blood colloid osmotic pressure, which describes the movement of water into the capillaries. Because of that osmosis, the water goes into the capillaries to go where the concentration of solutes are. So the solutes like albumin, they can't diffuse out of the capillaries. That is the movement of water into the capillaries, which is known as BCOP. And so we also have another force that is called ICOP, which is the movement of water outside of the capillaries into the interstitial space. So this is interstitial colloid osmotic pressure. And so we have the balance of each one of these movements. So just like in the artery side, we have the venous side. We will show here the hydrostatic pressure, the ICOP, and we will show the BCOP traveling into the capillaries. And so what I'll go ahead and do here is make a little bit of a table kind of describing the average pressures, the numbers, to kind of show this movement here. So another pressure to add here, what we have is these lymph vessels, and so this pressure will be caused by the lymph vessels kind of suctioning water out of the interstitial space and going throughout the rest of the body. So this is the interstitial fluid pressure that is from the lymph vessels. So which each one of those pressures will go ahead and describe the net movement based on the numbers. So here I have drawn out the average numbers of the pressures of the movement of each one of these types of pressures of the artery and the vein. So going in, we have an average of 28 millimeters of mercury for BCOP, 30 for HP, 8 for ICOP, and 3 for IFP, showing a total of 13 millimeters out is our average. On the venous side, we have BCOP at 28, HP at 3, ICOP at 8, IFP at 10, which shows an average of 7 millimeters in. So those are the average numbers based on the pressures that we have here. Okay, so now we're going to talk about edema and the 4 causes of edema. So the first one is increased hydrostatic pressure will cause edema here. So if we go look back at this diagram, say we have a really powerful direction of blood flow that breaks past this sphincter, there will be an increase in the release of hydrostatic pressure into the interstitial space. And so if this HP goes up and there's more liquid leaving the capillaries than can be taken up through the lymph vessels, then we will have edema or swelling. So the second cause of edema is increased permeability of cells. So this is the example of if there's an injury, if you have some damage or something on your skin, if you have a cut, then the cells along your skin, the proteins in the cell will go into the interstitial space, which will cause the exit of water. So the water will go to the interstitial space to regulate that increase of solute, which will ultimately cause edema. The third cause of edema is the lymphatic system blockage. So this is describing here these lymph vessels. So if there's a damage to these lymph vessels and they're not able to take this fluid away from the capillaries and from the interstitial space, then there is going to be a buildup of interstitial fluid here, which will cause edema as well. Last type of edema that we will talk about is called osmotic edema. And that is where if you have something like the dilution of your plasma, that means that it will have more water running through the blood, which will then in turn lead to more water exiting in the capillaries during this capillary exchange. So if you have dilute plasma or more water entering in the blood flow, that means that more water will leave the capillaries into the interstitial space, which will cause edema as well. Okay, we're now going to describe what is known as the baroreceptor reflex, and we're going to talk about the different components that make up this reflex and how it works. Firstly, we have the receptors, which are baroreceptors, obviously. And these are stretch receptors, so they respond to changes in the stretch of the arteries, and they will be able to change the blood pressure based on the stretch that they feel. So the second part, we have the afferent pathway. And so the change in action potentials due to these stretch receptors will be sent to the brain via cranial nerves. So third, we have the integrating center, which in this case is the medulla of the brain. And here we have cardiovascular centers that work to regulate the strength of contraction and frequency of action potentials that are being received. So number 4, we have the efferent pathway. And this is where parasympathetic and sympathetic nervous system will travel to the heart. In order to regulate the contraction, blood pressure, and the things that are happening based on these baroreceptors. So number 5, we have the effector organ, which in this case obviously will be the heart. And so based on these baroreceptors, we will have a signal being sent to the brain, and then the brain will then communicate with the heart, telling the heart what it needs to do. So if those baroreceptors are stretched and that vasoconstriction happens, then the blood pressure will go up in the heart, and if we have a sudden drop in blood pressure, we will know that the heart needs to increase its pumping and increase its cardiac output too. So in this question, we're going to be talking about the different types of regulation: the blood flow regulation, myogenic regulation, and paracrine regulation. So first, starting with myogenic regulation, we know that this is due to the smooth muscles around the veins and arteries that are able to contract because of stretch. So we know that there are mechanically gated channels that cause a contraction cascade which will ultimately lead to vasoconstriction and reduced blood flow. So now talking about paracrine regulation, we know that endothelial cells release paracrines due to an increase in metabolic activity. So this increase in metabolic activity will cause the release of paracrines like nitrous oxide, which will end up causing vasodilation, which will lead to an increase in blood flow. In this process of increasing the blood flow to replace more oxygen from CO2 is called active hyperemia. So now we also have what's called reactive hyperemia, which is when there is no change to metabolic activity. But this is what can happen with, say, an injury or something like that, where there is an increase in CO2 and a decrease in oxygen in the blood. So that will lead to this vasodilation and increased blood flow.